Welcome to the ForecastBuilder training on forecasting precipitation type and a microphysics review. This module was designed to review and set a base for precipitation type forecasting in the winter. It's complex and we obviously can't cover all there is to know here in this module without you spending the night and probably the next few days. But we're going to try to hit the high points in a short amount of time. And we hope to give you an appreciation for the unknowns in these environments and why probabilistic forecasts allow us to better describe outcomes and communicate scenarios. We all know that forecasting precipitation type can be very challenging. Uncertainty is pervasive. Both our science and forecasting techniques have grown over the years, but there's still a lot we don't know. These include observational errors in measuring the state of the atmosphere, modeling imperfections in the precipitation type algorithms, or the microphysics parameterizations that the models have, and gaps in our current knowledge of precipitation type behavior. All contribute to inaccuracies in the forecast. How about you out west or in terrain? Improper model terrain or how a valley is represented causes additional complications. Even in the very short term, many of these uncertainties can remain unresolved and are compounded by using a deterministic framework. It is unlikely you're going to find the silver bullet that gets it right. Sometimes I think of deterministic forecasts as highly detailed, inaccurate forecasts. So forecasting precipitation type is one topic where probabilistic forecasts and an ensemble of models allow us to better determine more or less likely outcomes. Forecasting precipitation type can be best visualized through an approach where you become the hydrometeor, from the birth to arriving at the surface. Maybe your Sue has a costume you can borrow to become a hydrometeor. All right, not serious. In any case, visualize the hydrometeor beginning within any saturated layer and then falling vertically. Consider this a top-down process where as a forecaster, you evaluate hydrometeors at the highest level, their phase, and then changes that happen along their path to the surface. Will they begin as ice aloft? Will they encounter an elevated warm layer? Does the warm layer matter? What about a surface refreezing layer? How will that alter the hydrometeor further? Near the surface, can we melt incoming ice crystals? Or possibly cool the layer to allow raindrops to freeze on contact? We're going to briefly review some of these concepts in this module, but I would ask you to consider if a deterministic model approach is the best way to handle the complexities we discover in the slides ahead. Let's talk about what we know from research and observations. There are basically 4 different thermal profiles that influence hydrometeor state, or what we affectionately call precipitation type. The first is pretty straightforward, the all-freezing sounding where ice is nucleated and falls toward the surface. If a surface-based warm layer exists, as shown in example B, and depicted by the red ME or melting energy layer, the ice crystal could melt to rain or a rain-snow mix depending on the magnitude of that layer. For those sites with terrain, this scenario can be handled using the snow level as a diagnostic. Another complexity is added in example C, where an elevated melting layer and surface refreezing layer are both present in the environment. These layers now bring in the possibility of ice pellets and freezing rain. Finally, the granddaddy of them all, the 3-layer Big Mac of the precipitation type world where uncertainty can reign. 2 melting layers and a refreeze layer sandwiched in between. That's just chaos to me. These forecasts are incredibly difficult. In the next few slides, we're going to dive into a few of these scenarios, beginning with understanding when ice nucleation is most probable within a saturated layer. The published research from aircraft icing studies in the field has informed us with a wealth of overlapping and corroborated measurements of the likelihood of ice nucleation or the beginning of the ice growth process in these layers when ice is first born. This diagram summarizes the research and suggests that as you cool from about -7 Celsius to -15, your likelihood of having ice introduced into a saturated layer increases rapidly. By about -12 Celsius, the probabilities suggest about a 70% chance that ice will be found within that cloud layer. Likewise, these data and this curve helps us understand that in the 0 to -7 range, that warm side of the curve, or that warm side of this diagram, there is very little chance to no chance that ice will be found in that layer. So in these situations, supercooled water would exist. One final note, while this temperature range for ice nucleation has some overlap with the dendritic growth zone for ice crystals, which is typically that -12 to -18 Celsius range, these two processes are different. One is of growth and one is of ice initiation, and they shouldn't be interchanged both in your mind or your conceptual model. Freezing drizzle environments are great examples of saturated layers where ice nucleation has failed to occur. So in this sounding example, it's clear that the cloud layer is in the -7 Celsius to -3 Celsius range, making it a high confidence forecast of supercooled liquid cloud. And if it precipitates, freezing drizzle would be the outcome. So also, it is well separated from any ice cloud aloft that could seed ice crystals into that near surface supercooled liquid layer. We're going to discuss that process at the end of the module. So typically, the challenge with these forecasts is if that saturated layer will grow cloud droplets large enough to cause precipitation. That's usually the warm cloud process or collision coalescence process. Research would suggest that the cloud layer depth should be at least 1 kilometer deep as an entry point for considering precipitation from that layer. Typically, deeper supercooled liquid layers and more vertical motion within that layer will increase the likelihood of precipitation. So let's get back to talking through the scenarios with forecasting precipitation type and hit on example B. This scenario, one melting layer, is fairly typical in transition seasons and in the western United States. While it's pretty straightforward that as the melting layer energy of the surface space layer increases, the more likely you are to see rain versus snow, diabatic processes can overwhelm the melting layer. For example, heavy precipitation rates, especially those associated with convective processes, can cool the melting layer through sublimation and evaporation as heat is transferred from the environment to the hydrometeor. So this yields colder precipitation type outcomes. So for those offices that use snow level as a diagnostic for rain or snow, heavier precipitation rates lower the snow level, causing snow on mountain passes once you maybe thought would be in the rain zone. So with these complexities, you now have another couple reasons that probabilistic space best serves precipitation type forecasts. Complexity increases as we consider case C, the elevated melting layer above a surface-based refreezing layer. This scenario can present itself almost anywhere, although it's most common east of the Rockies and the Conus, and to a lesser extent in the sheltered or narrow valleys in mountainous regions. These valleys provide the possibility of a very small but meaningful refreezing layer, leading to freezing rain outcomes. So focusing on the sounding example and tracing the hydrometeor from the top down, as the melting layer energy or area increases, here shown in red, the ice crystals falling into that layer have a high probability of melting into a liquid drop. As that liquid drop, or it could be kind of a mix, right? It could be a liquid drop with partial ice in it remaining, continues to fall, it encounters that refreeze layer here shown in light blue. And as the refreeze energy increases, so do the probabilities of complete refreeze of the liquid drop into an ice pellet. But the atmosphere is complex. So figure 5 here from Burke allows us to visualize how these layers interact and probabilistically. Each point on the graphic is an observed case, and the melting layer is plotted along the bottom axis, with the refreezing layer energy along the vertical axis. The triangles in the bottom portion of the graphic show that when the melting layer dominates, freezing rain is a high probability outcome. Likewise, moving vertically, the refreeze layer increases and ice pellets become more likely, as seen by the blue filled circles on the graphic. In between those two, a mix of both freezing rain and ice pellets occurs. For very low values of melting layer energy, highlighted by the green box, complete to various degrees of incomplete melting of the ice crystal occurs, which can refreeze to various precipitation types, and it's probably an environment best handled with a mixed forecast. Environment context is important to forecaster confidence. Even in high impact precipitation events, you may be in a parameter space that allows you to message outcomes or impacts more confidently, while other events, not so much. Take, for example, events with a warm layer aloft that are pretty robust, where the melting layer energy dominates the low-level refreeze layer. The lowest portion of the graphic, highlighted by the green circle, shows events that are nearly 100% freezing rain. These events are less sensitive to model inaccuracies and represent a more stable forecast. To kind of show that, for the points kind of in the center of the green oval, changes of, say, 50 joules per kilogram, if you add 50 joules per kilogram, for example, in the refreezing layer, still yield high probabilities of freezing rain. So this provides a high level of forecast confidence because even with some model error, the outcome type is stable and probably won't change. Conversely, some environments fall in gradients or transition zones. Here, the orange ovals show where the forecast confidence is lower, and a mix with various precipitation types and probabilities is probably your best forecast. So don't get bogged down too much in the details on these forecasts or try to pick a certain outcome. Just settle on a sweet spot in the probabilities to reflect the mix that's likely to occur. As we near the end of this module, it's important to cover a few considerations when forecasting precipitation type. Cedar feeder cloud processes are important to precipitation type outcomes and typically live in weakly forced events or during the early phases of precipitation onset prior to deep saturation. Supercooled liquid drop layers can rapidly transition to ice when ice crystals are seeded into the layer from above. So this process occurs on the order of minutes and not hours. It doesn't take long. This sounding shows the well-defined separation between the two layers. And if this distance is too great, or ice crystal density coming out of that seeding layer above is too low, or the separation layer is very dry, ice crystals can sublime before ever reaching the liquid layer below. But higher probabilities for the cedar feeder mechanism to activate are found as that dry layer depth decreases from about 2 kilometers to down to near 1 kilometer. If activated, the type changes from freezing drizzle at the surface to snow within about an hour. Hydrometeor size can also influence how readily it changes state. Larger ice crystals need more energy input to melt, and larger liquid drops are more challenging to refreeze than smaller ones. However, if liquid drops still have some ice in them, they will more readily refreeze. Man, it's just so complex, and just another example of why these forecasts are difficult and best handled probabilistically. Convective processes can change the game altogether in precipitation type scenarios by providing localized ice initiation into the environment. Elevated convection above a liquid supercooled layer rapidly transitions to a frozen outcome of snow or ice pellets. And it's kind of transient in space too. It can be a real problem forecasting and trying to resolve that in our forecasts. So hopefully from this module, you've gained an appreciation for how sensitive and complex these precipitation type environments can be to forecast, and that they're best handled through a multi-model ensemble and probabilities of precipitation types. These resources are available for you if you have any further questions regarding this module. Thank you for your time and attention during this presentation.